before I forget. Okay. So we're going to be talking about central tendencies, which is something that you learn in like elementary school usually, and then they kind of mention it in algebra, and it's mean, median, and mode. Plus we're going to go into some more advanced versions of that, and then we're going to talk about representing data with these terms and sort of what can happen. So they do mention it in statistics, hopefully. I mean, come on, that's like the most basic statistics there is. Right, and in Algebra 1. Okay, good. So Algebra 1 mentions it. That's good to know. Like, let's start off here by put a 1 in the chat if you've ever made a box and whiskers plot and you thought, what a useless thing this is. Or you just made a box and whiskers plot and had no opinions about it. Riley's like, lots of useless ones there, right? Andrew, yeah. So, right, those are the kinds of things here that we're going to talk about in terms of... Oh yeah, hold on, I got someone in the room here. So you're gonna have to mute. There you go. Okay. So, I'm back. Mean, median, mode, and range. Oh yes, okay. So box and whiskers plots seem sort of weird, right? People are like, why do we use them? Then all of a sudden, if you go into college or you do any kind of science in college, they're like, oh, make a box and whiskers plot. Like everyone just knows how to do that, right? We're not going to make a box and whiskers plot today. Although I know you guys are sad because I just hyped them up, making it sound like they're pretty cool. Let's see. Sorry, someone just said something in the chat and I just X'd out of it. I've had many things where it's like, when am I ever using it? Yeah, right? And that unfortunately will happen sometimes in school, right? But you really got to think about the bigger process here. Is the thinking that I'm doing applicable, right? And that might not be so obvious, right? Like especially in math, a lot of the stuff you're doing is learning how to logically think and problem solve. Are you necessarily going to encounter a word problem where they ask you about somebody buying grapefruits at the store, right? No. But are you going to use that thought process in solving other problems? Yes. And you guys know you've met people who you've tried to solve a problem with maybe, and you're like, what are they doing? Why are they doing this complicated hard way when we could be doing it really easily, right? Okay, excuse me. So, central tendencies and mice. So we're going to talk about mice again. Our objectives for today are to review central tendencies, mean, median, mode, expand on central tendencies, right? We're going to learn 2 new kinds that you maybe have learned in statistics in Algebra 1, variance and standard deviation. There's other ones, right? But we're going to focus on those 2. We're going to apply this to a real-world scenario of mice tail length, and then we're going to discuss the best ways to use central tendencies. So what is a central tendency? So let's have some brave people define for us in the chat or speak. Defining mean, median, mode, and range. Do I want you to turn off your LEDs? No, you can leave them on. It's not bothering me. I don't get easily distracted though, so I don't know. Maybe someone will let us know if it's distracting. But let's get some definitions for mean, median, mode, and range. All right, Destiny jumping in with mean. Mean is the average of the data set. I'd say we agree with that, right? So mean, the average, right? How do we calculate? We add all the numbers up and divide by how many there are. Okay, what about median? Median is the medium or center of your data. Okay, so how do we find the median? Does anybody remember? All caps. Median is the middle of the data. Yeah, so median is the middle or center of the data. How do we calculate that or find that? It's not really that easy to do, right? Unfortunately. Does anyone know how we calculate the median? Before we move on, I'll write the mode while we wait for someone to maybe suggest how we're doing median here. Okay, Alexandria says you put the numbers in order from smallest to largest and find the number in the middle. Yeah, right? It's not easy. Destiny said something similar there. Line up my data and pick out the one that's in the middle. So that sounds fine if you have 10 data points. If you have 400 data points, right, that's not going to be as fun. The nice thing is computers and calculators can do these things for us, right? So we don't have to worry so much about lining up all the data and crossing off one by one till you get to the center. And the good thing is you usually don't end up getting this, you know, they're not going to give you 5,000 data points to do this with, hopefully. So mode is the most frequent number. Yeah, you'll fall asleep trying to find the center. Exactly, because it's really hard. And if there's 2 in the middle, you find the means of the 2 numbers that are in the center. That's true, Destiny, right? So if you have 7 and 8 in the middle, then your median would technically be 7.5. Okay, mode is the most frequent number. That one's a little easier, right? Because if you see 100 happening a billion times, you go, oh, 100 is the mode. Sometimes there is no mode because every number happens once. And range is the minimum and the largest. It is, right? So range is sort of how spread out is the data. So we'll say min and max, right? Range can be, well, actually, let me ask you guys this. Why would range be important? Why would we care about range at all? Yes. I'll come find you after. It's important for plotting. Yeah, graphing is definitely a reason we want to know the range. Because if we're making the scale for our graph and our first number is 300, we're not going to start at 0, right? Because then we're going to have this huge empty space where we're not putting anything. So you can nail a sniper shot from far away with the range. Well, that would not necessarily be the range of a set of data, right? That would be a range as in how far away something is. Exactly, different type of range, right? So good to note that there is a difference between statistics range and regular range, right? Like home on the range kind of thing. No, we're talking about statistics range here. Okay, so yeah, it's important for graphing, right? It can also show you outliers. For example, if the data ranges from 0 to 100, right, but most of your data is in the middle, then really the range is going to kind of tell you that there's some outliers there. Okay, so that's fun. We know those definitions. Hopefully that was kind of a review for you, right? Mean, median, mode, and range. So now let's talk about more advanced central tendencies. Variance. Definitely write down this definition of variance because first of all, you're going to say, oh no, when you look at the equation, and then I'm going to show you that there's a calculator online that will do it for you, Riley, so you don't actually have to calculate it yourself. So variance shows you how far spread out the numbers are from the mean. So what would that mean? We're going to say mean a lot today, by the way. If we have some data, and let's say our mean is 10, right? So the average of our data is 10. Variance would tell us, is the data really far spread out? Do we have points that are 110 and negative 40, and yet somehow our mean is still 10, right? That's important for us to know. Versus are all the numbers kind of around 10? Because then there wouldn't be much variance. They're all close to the mean. So let's think about a real life scenario. Test scores, right? Has anyone ever had a teacher who would show you like statistics of the test score before handing out your test? I have a few teachers like that. They'd be like, here was the mean of the test. Here was the mode of the test. Here was the variance of the test. And then you would just sit there and be like, okay, what did I get on the test? I don't care about this other stuff. So let's say that we're doing a math test, right? And let's say the average on the test was a 62%. Okay, that's cool. The average was 62. If we have a big variance, which I can't spell, that could mean that maybe somebody got a 10 on the test and somebody got 100 on the test, right? So that's kind of important because if you got a 10 on the test, Well, clearly that meant you didn't really know what you were being tested on, right? But that's really far from the average. If we had a small variance, then maybe our lowest score would have been a 60 and our highest score would have been a 75, right? I don't know if that would actually average out to 62 if we had a bunch of scores, but just as an example, right? So that variance could be important here to know, because if you really did get a 10 on the test, telling you that your average on the test was a 62 for the class isn't actually going to tell you much about your score if the variance was big. Okay, so that's what variance is. How far away from the mean are the scores? Then we have something called standard deviation, which again, by the way, the formula is written here. We're going to have a question on the assignment associated with this where you can either A, for bonus points, work this out by hand, right? Following the formula and plugging in. You can do it. It's a formula, right? It might take you a little bit of time. You might have to watch a video or two on YouTube, but you could do it. Or there's a calculator online that you could have calculate it for you, and then you will interpret what the number means. So that's a formula for variance. What you end up doing is you take your mean, which is represented by an X with a line on top of it. That means the average or the mean. And you take a term in your data set, so any number. You take your number that you're looking at, you subtract the mean, you square it, and then you divide by the sample size minus 1. So if we had 15 numbers, you would do 15 minus 1, so each time you would be dividing by 14. Right, so this formula actually looks scary, but isn't that bad. And it's the sum, right? So you would have to do this for each data term. So if you have 10 data points, you would do this 10 times and you would add them all together. That's what that giant Greek letter here means. It means sum. Right, so it's not too hard. Of course, this could be hard, right? Depending on how you feel about math, but all the stuff's defined right there. So you're welcome to try it by hand for bonus points, right? Or we'll use the calculator. So our second advanced type of central tendency, which I abbreviated as CT, by the way, in case you were like, what's a CT, is standard deviation, which, this is where it gets a little complicated. It is a measure of variance. Okay, so what was variance again? Variance was the distance from the mean, right? How spread out is the data? Standard deviation is a measure of that variance. Why would you put a radical? Oh, yes. Well, because standard deviation is more complicated, right? So it kind of tells you a similar thing to the variance. A small number for standard deviation is going to tell you that the data is clustered around the mean. In other words, most of the data is right near the average. If you get a large number, then that's going to tell you that there's a huge amount of variance, right? Or a huge difference from the mean. The formula is pretty similar. Guess what? It's basically the formula for variance, except that now you take the square root of it, right? And notice, we represent standard deviation by S. We represent variance by S squared. How could we get rid of that square? We take the square root, right? So these formulas are related. A radical symbol, Riley, is this square root. Okay? Yeah, square roots are rough. Hey, at least that's not like a cubic root or something. Right, the check mark, exactly, right? That is called a radical. Okay, so standard deviation and variance are very similarly related. One of them is that number squared, and the other one is the square root. Again, what do those things mean? We're going to work through it, right? It is a pretty small thing that we're going to work on. So now let's talk about the mean. How good is the mean? Okay, we love the mean. Why? Because we know what the mean means, right? But actually, right, if somebody tells you, oh, the average was this, you go, okay, yeah. If somebody said to you, the standard deviation is this, you'd be like, huh? right? So average is a really great way to talk about data. If we talk about the average height of something, if we talk about the average score in a test, if we talk about the average amount of time it takes to do something, that makes sense to you, right? That understands. That understands. You understand. It's easy to calculate, right? We just add everything up, divide by that number. There's no square roots, there's no sums, there's nothing crazy going on. But is it the best way to represent the data, right? That's what we need to ask ourselves. In that paper we read, did we see a lot about mean? Not really, right? They weren't like, well, the mean of our data was this. No, right? You know why? Because the mean probably wasn't a good way to represent the data. Otherwise, they would have been all over talking about the mean, because then people would have understood, right? So we're going to do an example here to kind of see what I'm talking about. Mice tail length. So we have these cute little mice. Pretend that they're real and not really fuzzy and soft. I collected some data on them. Oh yeah, these are cat toy mice for sure. We have two groups. We have our control mice and our experimental mice. Our control mice are given their regular diet, right? Whatever mice normally eat, which I don't even know what that is. Probably should have looked that up. Our experimental mice, right, which are in a separate cage, they are given a diet with a mutagen, right? In other words, something that is suspected to actually alter their DNA, right? A mutagen is something that would cause a mutation. So we think, as scientists, that it's going to alter the tail length, right? That's what we want to find out. So we're basically asking, okay, our control mice are doing normal stuff. Our experimental mice are eating this mutagen poison, essentially. Are the experimental mice having shorter tails? Yeah, it doesn't, it has legs. They're just in its hair. Okay, imagine. Okay, so here is the data that we collected on our mice. Because I was going to have you guys measure mice on the screen, and then I realized that would take way too long and would be hard. So I measured them for you. We have our control mice and our experimental mice. You guys right now are going to calculate the means. So let's have Alexandria, Caitlin, Christian, and Destiny. You guys calculate the mean for the control mice, right? You can each do it, and we'll just make sure we all got the same answer. And everybody else, you're going to calculate the mutagen mice tail length, right? So again, we're just finding the average here. Shouldn't be too hard. You're going to add up. You can use a calculator, right? So use a phone or use a computer calculator. You're going to add all of those up, and we're going to divide by how many there are, which let's see. There are 12. Whoa, Destiny's speedy. You were already typing it in before I even finished explaining.
It's really
I have a fan club here, guys, watching me talk about mice tail length. And my TA, who's supposed to be here.
Well, I mean, just to be here. If the mice are getting poisoned, would they just die?
Oh no, just their tails getting affected, but that's a good question. Okay, yeah, so we have a confirmation of Destiny's number for control mice. We got 5.5. Let's say these are millimeters, right? So our control mice have an average of 5.5 millimeters. What about for our experimental mice? Do we have anyone yet who's come up with our experimental mice average? Riley, divide that by 12. Sounds to me like you added them all up but did not divide by 12 yet. Lauren says 5.4. Do we have anybody to confirm 5.17 Riley got? 5.4 Elizabeth also got. Okay, so we'll go with 5.4. Riley, check your addition. You're very close to being there. Hey, it's okay. This is hard. It's 12 data points, right? It gets confusing, especially when a lot of them are really similar and I was talking, right? That can be confusing. So don't worry about it. We got our averages. Okay, so now our control mice have a tail length of 5.5, average. Our experimental mice have an average tail length of 5.4. Does there seem to be a difference between our two groups based on the average alone? No, right? 5.5 and 5.4, that's basically the same. Now, looking at the data, you see a difference. So tell me what the difference is. Looking at the data, what's going on? The others are scary. Well, how? Tell me what's going on. What data are we seeing here? Alexandria uses a great vocab term here. The experimental mice have a larger range. It's true, right? I see tails 1.4, right? That's really short. And then 8.8, I don't see any huge numbers like that in the control mice. Control mice are more centralized around 5.4, but in the experimental data, no mouse has a tail length of 5.4. So Destiny points out a really great point here. None of the experimental mice have a tail length that's close to the average, right? 1.8 is not close, 9.8 not close, 2.3 not close, right? You guys got to be quiet over there or you're going to have to leave. Okay. So none of the experimental mice have a tail length close to their mean, right? That's weird. The first group all have around the same tail length, right? Christian says. True, right? 5.4, 5.2, 6.1, all pretty close to each other. Okay, so if you're a scientist and you published a report where you said, actually, this mutagen doesn't do anything to the tail, right? Both groups had the average around 5.5. And, you know, it seems like there's no difference. The mutagen's not doing anything. Someone could publish that. And if you didn't see the data, you would go, oh, I guess that mutagen does nothing, right? If you look at the data, you would go, whoa, you're crazy. Why would you say that? Look at this data. The experimental mice tail, I would say it's having a difference. They're either really short or really long, right? So this is an example of a time when the mean is probably not the best central tendency to use, right? Or maybe not the only one. So remember our averages, or actually, we'll probably have to do multiples. I don't know how I'm going to get this to set up. Let's see. What we're going to do is graph it. So what would a graph look like? We'll go back. Looking at the data, I want you to sketch a graph. Does not have to be a perfect graph, a sketch, right? In fact, I'm going to sketch my own graph here. So making a scatter plot. So plot points on your graphs. Where on a piece of paper next to you, Riley, open a new window and draw one. If you have, you could Google whiteboard and there's one. I know I was gonna try to make like an interactive thing where you guys could draw too, but I didn't have time. Okay, so let's see. I'm trying to make dots and they're not really turning out very good. Okay. Regardless, for my control mice, my data set's gonna look something like this. Most of the points are gonna be clustered in the middle, right? Let's say this is 5. A really ugly 5, but it's a 5. Right, most of my points are gonna be clustered right around 5. There's not very many points over here. Okay, make sure you finish watching it, Lori. There's not a lot over here, right? Because there's no mice that have tails that are long or short. They're all in the middle. What about for our experimental mice tail situation? Could somebody describe what they think a graph of that data would look like, or what you're seeing as you're graphing it? You should be graphing, Riley. My day will be better when I see that you're graphing. Okay, so hopefully in your graph, you're seeing something like this. Most of the mice tails are clustered around, should we say 2 and 8? And as you guys expressed in words, right, none of the mice tails are representative of the mean. So our mean is right here in the middle. However, that's not actually representing any of the data from this data set, which is weird, right? So we call this a bimodal distribution, where it means that the data is split into 2 sections, right? A lot of it is represented on the low end and the high end, but none is falling in the middle. Whereas this is more of a normal distribution, right? We call it a bell curve distribution, where most of the numbers fall around the mean. And then, of course, there could be outliers, right? In fact, I think a better way to draw this than what I drew would have been to draw it like this. Because really, they're all clustered right around the mean. There's no outliers here. So that's just a way to think about representing data. So now I'm going to challenge you guys even further. Excuse my ugly graphs that are slowly going to get erased here. Oh, I know, I forgot I have to erase each one of these dots. Okay. That one just doesn't want to erase. Okay, so is the mean the best way to explain this data? We already talked about this, right? And we all pretty much, I think, would agree at this point, no. So I want you guys to explain in your own words an answer to this question. Is the mean the best way to explain this data? Why or why not? This is going to be me checking to see that you're understanding what we're doing. So just type a response in the chat, right? Yes, it's the best way. No, it's not the best way. And why? Good. Destiny gave us our first explanation here. It's good for explaining the control mice, but not the experimental, because the experimental mice are on a lower end and a higher end rather than around the middle, right, or around the mean. Good. We'll give everyone else a couple more minutes here, or seconds, to formulate those thoughts, right? Is the mean the best way to explain this data for our mice? Good. Elizabeth says they have 2 very different ranges, so it's not a good way. Christian says, when we got the answers for both graphs, they were almost the exact same despite the different pieces of data. We need a more accurate way to show the dramatic ranges. Good. No, it's not, because the data is all over the place, because the control is good and the experimental is high and low. Okay, good. Not for the experimental mice, because the change between them is too drastic. Yeah, exactly. You guys are getting it, right? So in this case, if I told you the mean and the range, would that be enough? Riley says no. So let's say I told you the mean is 5.5, the range for the experimental is from 1 to 8, and the range for the control is from 4 to 6. Does that give you a better picture of the data? Kind of. We're getting better, right? At least then you're like, whoa, the range on that experimental group is huge. Seems a little intense, right? Let me look at the data. Now, of course, we're talking about a data set of 12 points. Imagine that we did this in a real science experiment where we collected data over the course of a year, possibly, or maybe even longer, and we had, 1,000 data points, right? If we had 1,000 data points, are you going to be able to just look through all 1,000 data points and see a pattern? Maybe, right? Maybe not. So this is going to get harder and harder as you actually gather data. So Riley, what I'm talking about is that telling you the mean and the range here probably gives you a better idea of what you would see, but isn't 100% there. So based on the new vocab we learned, variance and standard deviation, what if I told you the variance of the data or the standard deviation of the data? So, oh, thanks, Winter, for your response there. The mean is not the best way because there's a lot of numbers that are pretty far. Good. So what if I told you the variance or the standard deviation, how far away from the mean these data points were? And I said, well, actually, the experimental mice had a huge variance. None of them fell on the mean. They were all really far away. Would that tell you more about the data? Yeah, right? So then this is a case where we would probably actually need to also include variance or standard deviation or both, honestly, because then that's going to give people a bigger picture of what the data actually looks like without having to look at the data yourself, right? Because the point here is, do we want to spend our time analyzing data? No, somebody else should have done that already, and we want to make sure that what we're understanding is correct. Okay, so now we're going to do a little challenge. Which type of data is the mean not good for? So I want you on a piece of paper, or you can Google whiteboard, I want you to draw graphs of data where you think the mean would not represent the data well. And I'm going to give you one example. My crooked graph. That's my example of a line graph where I don't think the mean would tell us very much about the data. And unfortunately, I'm not going to be able to really see what you guys are drawing, which I didn't really anticipate needing to see what you're drawing. So if you want to hold your drawing up, we can try to see it in the camera maybe. Oh, a circle. Yeah, well, how would that graph look though if data was making a circle? It's kind of weird. I guess the mean wouldn't be representative there. I'll agree with you on that. So a circle, sure. Anybody else have an idea for a shape? You could even describe it to me in the chat if you want. And I can try to draw it here. Oh, I see. Good, a picture where there's just a crazy scatter plot, right? So there's just dots all over the place where there's obviously a big range, a bunch here, a bunch there, right? That, the mean wouldn't tell us anything about that. That's true. Did anybody draw like a crazy, like something like this? Where we have a million peaks, right? Yeah, where it goes up. Okay, perfect. Yeah, that's exactly, right? Is the mean going to tell us something about that? No. Now, here's the thing I want you guys to do. Next time you're reading an article, because you see this a lot, you don't even think about it, and somebody mentions the average or the mean, I want you to actually think about, is that mean really representing the data that they're talking about? And really think about it, right? Because they might be using the mean to try to prove a point, even though the mean doesn't actually represent the data. You drew a rectangular plot with random sized rectangles. Yeah, right? So the mean doesn't always work. Now, it does sometimes. We like it when it works because then it's easy. The point here is not all data can be represented by the mean. So here's what you're going to do. You are going to create your own data set of at least 12 points, right? So like I created the mice tail data set, you're going to create your own data set. Now, does it have to be two groups that you're comparing? Not necessarily, right? It could just be one group. If you want to create a concept, right, where you have an experiment or something like that, it could be. Random numbers, sure. It could be random or it could be a concept, right? Like maybe you want to do height or, I don't know, something else. Weight, something like that. Shoe size, right? Whatever. Any concept you want or random numbers is fine, right? You're going to describe, based on the numbers that you generate yourself, what central tendency is the best to analyze your data set. So is the mean the best? Is the mode the best? Is the median the best? Is the range the best? Is the variance the best? Is the standard deviation the best? Or is it a combination of 2 or 3 of those? You're going to include your data set, a graph of your data, and a description, right, of what central tendencies actually fit. Where do we do the graph? So you can do the graph on paper, right? Or there's a few graphing websites. I know there's Desmos, right? What's the other one that you guys use? Trying to think about what the name of it is. I see graphs from it all the time. GeoAlgebra, yes, right? So you can go to those sites, Riley, and you can type in your data and it will graph it for you. If you do it on paper, you're going to need to take a picture and put it in your assignment to get full credit. Or you could email or text me the picture. So I know some people don't like graphing by hand. That's fine. You can graph it on one of those websites, right? Then you're going to calculate the variance or the standard deviation you can choose for your data set. And you're going to calculate the mean. Mean should be easy. You're going to add them all up, divide by however many you have. Variance and standard deviation are going to be a little harder. What noise am I hearing right now? Okay. So you can do it by hand based on the formulas that we saw, right? Or I just added into Canvas because I realized that I forgot to add this in before. I just added in 2 modules. Let's see. I added 2 websites that will calculate the standard deviation and the variance for you. Having a hard time scrolling. Which if you go to lesson 7, central tendencies, you'll see the PowerPoint, right, that we just went through. And then if you scroll down, you will see these 2 links for a variance calculator and a standard deviation calculator, right? You're welcome to use those, right? I'm not concerned necessarily with you being able to do the math here. I want you to understand the math. So whatever number you get for your variance or your standard deviation, see if you can figure out what that means for your data. The question that you're going to need to interpret from this for the test, which I know Christian already took, right, is why the mean isn't always the best. So at the very least, make sure you're understanding why the mean may not represent the data. If you also understand variance and standard deviation, that makes me happy, right? But I'm not going to test you on calculating those or interpreting values from those. It's just to show you, right, that central tendencies go beyond mean, median, mode. These are actual things that people use, and they can be important for actually giving you information about data. Okay, so otherwise, the next thing you guys are going to do is take this Module 1 exam. on all this statistics stuff. The practice problems will help prepare you. Christian, you want to give anybody some advice since you took the test already? We'll see if Christian has any advice for us who haven't taken the exam yet, right? But there will just freshen up on statistics and especially the stuff we're going over right now, okay? Right, you are gonna do a chi-squared calculation. You are gonna do an R calculation, right? You can use the R calculator for chi-squared. You can use the data helper. But those are worth 20 points of the exam, so that's a lot, right? So make sure you know how to do those. There is a question about the mean, right? So make sure you understand why the mean maybe isn't always the best representation of the data. And then otherwise, that's pretty much it for today's virtual session. Does anyone have any questions before we go? What do we do for the chi-squared? So there is the chi-squared data helper at the end. Oh, you compare your value to the critical values. There's a chart on the chi-squared at the bottom for the critical values. If you need help with chi-squared, go back to the M&M lab and watch that video. Right? You can always skip through parts of it that you don't need. But do you find the mean for chi-squared? No. Good question. For the total, no, you just add them up. That's a good question. Yeah, so you don't find the mean in chi-squared, you just add them up. It's, again, one of those sum ones with the little E thing. Okay, other questions? You do practice problems, let's say, and you get stuck on something, right? Send me an email. Send me your document. Say, hey, I'm stuck on question 3. I think I did this wrong, whatever, and I will look at it and help you. So, Christian, you are going to be turning in the last thing that I just mentioned, assignment 1.7. You're going to create your own data set of at least 12 points. You're going to describe which central tendency is the best to analyze your data set and why. You're going to include your data set, a graph, and a description for full credit. Then you're going to calculate standard deviation or variance. If you click on assignment 1.7, which is due today, I believe, it will give you all those instructions again. Okay. Other questions? Okay. If you think of a question, email me. And otherwise, I will see you guys next week at our regular virtual session time at 10 a.m. Okay? Bye. Oh, code word. People left already. That's okay. There's no code word for today, which is what I was going to say, because since we did the time shift, I know some people couldn't come because of that. Right? So everybody can get full credit for today's assignment. Okay? So I will see you guys next week.